Okay, we're back. And what I want to do is go back to page 108 and wrap that up and get into those questions at the end of the chapter, which is only another 2 pages. Okay, so I'm getting rid of this here. And pretty much everything we've covered summed up with these two little formulas right here. Okay, now back on page 108, they mention pneumatics. Remember, that's a study of, they call it compressible gases. Usually, for us, it's usually air. And they mention a shallow well pump depends on air pressure to force water from a well. That's interesting. I had a shallow well pump. They're very rare. It's only good down to about 25 feet, a single well pipe, what they call a shallow well pump. And because it uses like a suction to pull the water up. Anything over 25 feet, it doesn't work too well. Now, in this chapter in here on well pumps, which we did on water on well pumps, if you remember that, they mentioned 25 feet is about the maximum depth that you want to go with a shallow well pump. We talked about the expansion tanks and that, so let's leave that alone and move on to airlocks. Now, on page 108, top of the page on the right there's a picture of an airlock. Now, as soon as I saw that, what I thought about is the heating systems. The heating systems that my generation put in, like 40, 50 years ago, 45 years ago, we used, and you're all familiar, you guys that do hot water heat, I'm sure you're familiar with it because probably the majority of the systems still out there, other than the new systems, of course, are the old style. Now, the old style system worked very well. For those of you who haven't been around or haven't seen it, I'll show you. You got a boiler here, and it leaves the boiler, right? I'm going to skip all the controls. Baseboard, and it comes back. And right here, we got a circulator and into the boiler, right? Very, very simple. Now, it works very well, but there's a problem. If there's any air in this system here, right, the circulator is designed to push water around or pull it, just actually pull the water and just keep pumping it back into the boiler, right? And around it goes. If you get a slug of air up in here, like where it goes up and then over, then back down, then to the next room and so on, you get some air in there, it's not going to work. What you hear at first, this is a good one to keep in mind. You got a customer who says that the heating system is making a lot of noise. They can hear the water in the pipes, but they're really not hearing the water. Before it quits working, it gets all kinds of air bubbles going around. It makes noise. It makes a lot more noise than it normally does. Normally, the heating system is very quiet. You might hear that little dinging from the metal expanding copper pipes. If they were wedged in, they might start creaking in the floor. Or those little aluminum fins, if they're touching each other, they might start making a little bit of noise, but not bad. But once you get air in there, mixed in with the water, because somehow air got in there into the system, at some point, it's probably going to stop working, right? Sooner or later, there'll be enough air in there that when the pump is pulling the water around, it can't pull anymore because there's air. And this pump won't pump air. It only pumps water. Okay, so now I have not done this, so I haven't seen exactly how it's hooked up. Let's take this circulator out of here. Right? And I don't know the connection. I'm going to have to go look at a new job. We'll put the circulator right here, like that. Now, here's the good news. Now it's pushing the water. And there was a book out when I was still teaching, maybe 20 years ago. I saw this book. I retired about 12 years ago. Anyway, and it was called Pumping Away. It was pretty new at the time, new theory. And they had a system where the circulator was near the beginning of the system. I don't know just where, but near the beginning. And if you got air up in here, it wasn't a big deal because this was pulling water right out of the boiler, okay? And it would just push the air right around and back in, and then it would go out You know there's a float air vent usually right on the system right here. There might be another one up where the external tank is, right here, right? You know that there's a little float air vent there, maybe one here, right? Could be anywhere, but usually there's one here and one here. So any air that's in the system will probably go out. Now, one problem could be that somebody inadvertently shut the water supply off to the boiler, and the water pressure coming in, which is usually 40, 50 pounds, whatever it is in the house, and then it's reduced down by the pressure reducer to 15, 12 to 15, it says on the tag, but it's usually 15 to 20. Now it's not even 12 to 15. That's getting lower and lower because the water, believe it or not, actually evaporates through the seals, like the gaskets and things like that, over a period of time, but it takes a long time. Now, those of you who have done heating systems know that you have water come in, we'll say like that, with your shut off, right? Your pressure reducer and your backflow preventer, right? All in a row here. Backflow preventer, actually this would be the backflow preventer and then the pressure reducer. Okay, this is all plumbing right to here. But this you can all do without a license because it's heating. Okay, now believe this is you guys that have done heat aren't going to believe this, but my brother worked out in Wyoming for a while. It's like the Wild West out there, no licenses or any of that. And this here is all optional. So you're going to say, well, how do you fill the boiler up? The boiler drain over here, you just backfill it with a hose, right? Until you get it up to, well, we'll say 15 pounds pressure. And then you leave. Take your hose with you. Then a few years later, I guess you can come back and have a service charge to refill the boiler or fill it back up to 15 pounds because there's air in the system. But anyway, that's how they do things out there. But we don't do it like that. Even the old systems always had a water feed coming in. Okay, but this is the way I understand that you guys are doing the heating systems now. Unless you're working with an old guy, this is much better. All right, the old systems are good, but they're subject to that airlock. Okay, hold on a second. It's got to make a note here. Okay, that was page 108. And let's see, I just want to make sure I made a few notes on here before. I did cover all that without. Okay, and on page 109, they have some, it's interesting to read it. Look at that diagram on page 109, and it's kind of common sense. When you got water coming down a stack, it's pushing a little bit of pressure ahead of it. Example of this would be, I think you've all experienced this, if you're on what would be the top floor of a house, second floor, top floor, whatever, on an extremely windy day, you'll see the water in the bowl of the toilet kind of dancing, moving around up and down a little bit. All right, it's not perfectly still like it is almost all the time. And that's because the water is affected by the air blowing across the top of the stack at the vent terminal, right where it meets the air. You got air, wind blowing across there, changing the pressure slightly. And that pressure is enough to affect the toilet. Okay, so that's what they're talking about there. You know, there's a slight increase in air pressure. Oh, that's it. It'd be coming in from the outside. Doesn't cause a problem, but you can see it. Okay, let's get to the questions on page 110. Now, on page 110, it goes back to exactly what I had up on here before, which I've already erased. Let's put it back. One foot equals 0.434. Okay. So the first question is column of water 14 feet tall exerts a pressure of how much on the bottom of the container? Okay, so we got 14 feet times 2.31. All right. I don't know if I got the math right there. Let's see. 4, 12, 3, 1. Oh, I'm sorry. I was just testing you guys, see if you're paying attention. All right. 14 feet. I use the wrong formula. You got to use this one. All right. All right. That's 1 foot. We're doing 14. .07. Okay. Now, remember, they're just using 0.43. We're going 0.434. So ours is going to be a little bit higher, but not enough to make any difference. So the answer is right here. Okay? 6 psi. 14 feet. It's a little less than half a pound, half the height. So if you want a rough check on, let's say they give you a problem that's 200 feet high, it's going to be a little less than 100 pounds pressure. Okay? All right. And here it is here. It's 6 psi is 14 feet. So that's number 1. So it was A. Letter A is the answer. And you notice there's nothing even close to letter A. All right? Number 2. A column of water 22 feet high exerts a pressure of blank on the bottom of its container. Okay, they're trying to be a little sneaky here. We don't care about the shape of the container. Now, I don't know if I told you this. The shape of the container doesn't mean a thing. So let's throw that out right away. So what do we got? Well, we've got 22 feet times, right? Have to change markers here. Okay, now the book answer was 9.46. Again, because we go with this extra here, it kicks ours up just a bit. But the book answer was 9.46. Close enough. There's nothing else anywhere near that. Okay? Now what they do a little sneaky here. If you screw up on a decimal, they got an answer for, 94.6. So you mess up on the decimal, they got you. All right, I think they do that on the math test too. They'll have the wrong answer that you might have gotten because you were careless, like on a decimal, and you think it's the right one, you go for it. Okay, in this case here, if you got 22 feet, right? So 9.54 psi equals 22 feet. So you got from a sink on the second floor to the basement in the cellar would be about just under 10 psi difference. Okay, that was number 2. Number 3, the pressure head available at the base of a 50-foot water tower is, okay, again, they're playing with you here, 50 feet. That's it. All right, so it's 50 feet. Okay, it's the height. Now, one thing I don't think I mentioned, let's take a look at this. They talked about the shape of the container. If you have a a 4-inch pipe and you have a 1-inch pipe, or even make it a 1/2 inch, right? A little skinny little pipe right here, like this, and you got a big pipe over here. And you put a pressure gauge at the bottom of both, right? If this was 10 feet high, it would be 1 foot would be 0.434, 10 feet would be 4.34. So this would be 10 feet would be 4.34, and this would be 4.3. It's the same. Okay, so when you put a when you put a 2-inch piece of PVC or no hub, next time you do an underground job, that 2-inch piece of pipe puts 4.34 pounds pressure on the pipe you're testing. All right. Or if you put a gauge at the bottom like this, it comes up the same. All right. It's still 4.34 pounds per square inch. Okay. So the shape and the size of the pipe makes no difference. All right. Next one. Number 4. The pressure available at the base of a tower in the previous question is how many pounds per square inch? All right. So what they did is they just used that same problem. And what they're telling you is if the pressure is 50 feet. As soon as you say feet, it's 0.434 per foot. All right, that's the pressure. And what's that going to be? We got a 0. 21.7. Let me see if that's the right answer. Yep, that's the right answer. Now, the book called it 21.5. Again, they used a slightly less accurate. They skipped this. So that's the PSI we're looking for. All right, so for those of you keeping track on the answer, that was letter B, is number 4. Number 5, if a gauge attached to a hose, there it is, a gauge attached to a hose bib reads 35 PSI. There's that little gauge I was telling you about, the one you screw on the end. Some of you guys probably keep one in your truck. Hose bib reads, now they're doing the flip of this. If you got 35 pounds, okay, so the question is, if the gauge is 35 PSI, and you want to know it would match up to how many feet. In other words, 35 pounds of pressure will pump. If you've got a gauge that says 35 pounds, and you got a building that's, we'll say 150 feet high, and you got water at 35 pounds, you want to know how high is the water in that building. It's not to the top. You got 150 feet. But I wonder what floor the water is at right now. Well, let's do this. Let's multiply this times 2.31, right? Because for every PSI, 1 PSI is 2.31 feet. So if I had 2 PSI in a gauge, the water would be up 4.62 feet, right? 3 pounds would be 6.93, okay? Now, they're looking for 35 pounds, right? So let's do that out. Let's see. We're coming up with 80.8. They came up with 81. Okay, look how there's nothing anywhere in the ballpark. So letter D is the right answer. Okay? They gave you PSI, you're looking for feet. All right, so when they give you the PSI, it's going to be bigger when you switch to feet. Feet is always it's 2 times bigger and then some. Okay, so where would that be in a building? That'd be 8 stories high. So you go up 80 feet, it'd be like the 8th floor. That's where the water, if you could look into the pipe or you open a faucet, anything around this, right at this height here, if you got a faucet, that's exactly where the water would be if you could look in there, or you cut into the pipe. Okay, below that you'd have water coming out, and above that you'd have nothing but air. Okay, that was number 5. Number 6, if the pressure head is 28 feet, a gauge would record the pressure as what? Remember, don't let that pressure head fool you. 28 feet, let's see what that is. They give you the feet, so they're looking for PSI. So 28 feet times 0.434, like that. Okay? And I wish I had my calculator. But we can do the math. 8 times 4 is 32. See if that's the book answer too. Yep, that's the right answer. Okay, now the book gives you an assortment. So the pressure head is 28 feet. They're telling you how high up the water is, right? To the top of a water tank or whatever. It could just be a pipe. It's 28 feet high. You multiply that by 0.434. And 0.434 is 1 foot times 28. We got 12 PSI. Okay, now the reverse of that would be if you got 12.15 pound pressure at the bottom of some kind of stack, and you wonder, I wonder how high up the water is. It's not coming out the top. Well, you can do the math. Multiply. You want to know if you want to know what the pressure is at the bottom, you got a 28-foot stack of water. What kind of pressure we got down the bottom? It'd be 12.15. Now, this reminds me of something, and that's as good a time as any to do it. This was a job up near Boston, and I had to fill the whole house, and we had a basement bathroom. So we had basement bathroom, first floor, second floor. Oof. I think Mr. Spam is calling. Let me get rid of him. Oh, excuse me, sir. Hello? Good, thanks. How you doing? Yes. Sounds good. Okay, thank you. Sorry, guys, I had to get that one. That was the building inspector. He's coming out to check out my handiwork. Okay, so like I said, you get 28 feet. You want to know what the pressure is down the bottom? That's what it is. Now, here's the problem. I just thought of it. It reminds me of this job I did back in the early 80s. I had, and I think I told this story to some of you guys. I had a water closet and, the usual stuff in the bathroom on the lowest level, which was like a basement. Then I had a bathroom on the first floor and the second floor, and then the pipe out the roof. So it was at least that high. It was probably higher than that to the roof. Now, that's per square inch. Now, you take a water closet, it's a 3-inch diameter pipe. Let's say it was a square pipe. Making a square pipe, like ductwork. 3 inches by 3, like that, is what? 9 square inches. Okay? Now, because it's round, it's this, and you put a circle in there, like that. Now, what's the formula for this? The diameter squared, like this, 3 times 3. 785. Okay, remember that? Now, just to save time, I'm going to make that 9, 3/4 of 9, which is like 0.75. So 3/4 of that would be somewhere around 7. I think it's 7.06 if I remember right. So you got 7 square inches times 12 and change, right? You get about 85 pounds lifting up of water pressure, trying to get out of that water closet. Now, some of you guys have probably experienced this. Those of you guys who test job with water probably know that an inflatable plug is very risky on a low-level bathroom like this. Top floor, you're probably okay. But on the lower floor, where you're going to get the highest pressure, like this, in the basement bathroom, that's a lot. Now, that inflatable is going to come right out of there, right? Some of you, I'm sure, experienced it. So what do? If you got a wooden floor, you can get like a piece of ferrin 2x or something and screw it right into the floor, the subfloor, across the inflatable that you have in there, so it won't blow out. Or another thing, if you got just cement around there, get the heaviest box you've got, like your fitting box or a heavy toolbox or something, and kind of put some weight on there. Okay, there's an example of the high pressure. 12 pounds is nothing, but that's only on a square inch. But when you get the whole thing like this, you get about 7 square inches. So that's 7 times 84. If it was a square pipe, it was 9. Remember, that's where that came from. So don't forget that. For those of you who haven't bumped into this before, if you're going to be testing something, watch those inflatables. Okay. Let's see what else we have here. Okay, now these last two here, I'm going to cover them. And if I remember it, I mean, well, I'm going to be talking to you before you see this video. I'm going to send you, and it's late, I understand. I should have sent last week. And what it is they call it useful information. It's a whole section at the back of this book that I forgot about because we don't normally use it. And I don't think we've been referred to it this year. But if you flip, and I know you don't have your own book there, but if you go to the back of the book, it's got a glossary. So it's got like a really neat a glossary, like a dictionary, plumbing terms. Then it's got some charts. So what I'll do, if I remember it, I'll send you the 2 charts you need to do number 7 and number 8. But what they're doing is they're getting in deep into friction of the pipe and the how much resistance there is. And I think you're all aware of that. That comes into play in our gas code, right? Now, we've done quite a bit with the gas code. And if you remember, the distance is a big deal. And the further the distance is from the meter, the smaller the capacity for the piping. It's quite a bit smaller. So if you go from 30 feet to, we'll say, 120 feet, it might cut the capacity of the pipe, and I'm making this up, but about half because of all the friction for the gas moving through the pipe, which is the same as water moving through the pipe. There's a lot of resistance in there. So that's already factored in for us, both out on the job and even for tests. You need the chart. Now, for this here, this water part of it, that also was factored in, right? But at the residential, light commercial level, not a big deal, right? They don't really get into the distance. The size of the pipe is more what they get into in our plumbing code. So I'm not going to make a big thing of number 7 and 8. If you want to look it over and look at the chart that I'll send, if I can remember it, go right ahead. But I would not worry about that for your own exam. Now, also number 1 on the suggested activities, I took a peek at that, and I think it's 17 on page 594. And the second one there, I got impatient with it, and I never did get the answer for that one. But if you want to do it, those suggested activities we don't normally do, but you can check it out. Okay, now 252. Okay, I think that is it for questions here, and I wish I had you live so I could ask you if you had any questions, but I don't. So just a quick review because we only got a few minutes left. If you had 1 cubic foot of water equals 62.5 pounds, right? 1 gallon of water equals 8.33 pounds. Okay? 1 cubic foot equals 7.5 gallons. All right? This is water. This is anything. This is volume. This is stuff. Sand, water, doesn't matter. All right? So if you've got 7.5 gallons of something, we'll say it's water in a water jug, and you had it lined up, and you have a box that's open of a foot by a foot, just a cubic foot. My guess is that you'd win a bet because you'd never think that 7.5 gallons would fit in there, but it does. All right, and if you want to know how much a gallon weighs, you just divide this by 7.55 into here, and you come up with the 8.33. Okay, I don't have the calculator right here, but trust me, it would work. Okay, so these are a couple of other numbers that you need. Now, these are numbers that are not given to you on a test. They're not on a chart. This is what you have to memorize to work these out. Okay, and I remember what I told you about the cubic foot. If they told you it was a cubic foot of water, but the container was only 3 inches full, that's what, 3/12, 25%. So 25% of 62 was what, 15.5, I think it was. Okay? So, in fact, here's 5 really important formulas that you want to learn. Okay, guys, I think the inspector just drove up. Plus, I'm already done. Okay, I will see you in class. We'll go over it then.